Yeah, so hi. Today I will start about the week 7 assignment, which is assignment 7 of the previous year. So I will solve some op-amp problem during this session. So as we all know, this is E62 Basic Electronics class of Professor M.B. Patil, and I am Subhajit Basak, the PMRF Fellow from IIT Bombay. So I will start to solve the problem. Uh, yes, yeah. So yeah. Uh, okay. So today I'm going to solve some problem regarding the ideal op amp and regarding the non-ideal op amp, and mostly we'll cover the difference amplifier in the op amp section. Earlier we have done some analysis using the inverting terminal, inverting op amp and non-inverting op amp, but today I'm going to discuss about some difference, how the op amp can be used as a difference amplifier, and also I'm going to discuss about the some non-idealities that are present in the op amp and how it affects in the output voltage. Okay, yeah. So in the first question, it is given in the circuit shown in the figure, the op amp is ideal, so it is ideal op amp. And if the resistors have a tolerance of plus minus 1%, and then what is the range of VO? That means the resistor value R1 and R2 can be varied plus minus 1% from the value that is given. So often we face this issue, like exactly 15 kilo ohm or 1.2 kilo ohm resistor making is quite challenging. So it may have some tolerances, and that much tolerances, how it affects in the output voltage, that is the main concern. That if this R1 and R2 varies too much than 1% or something, then how much voltage that will appear, that we can calculate also. And also we can say that whether the with this variable register or some deviation of the register, will it be work as an op amp, or will it be meet our case or not? Okay, okay. So in the first question it is given like this R1 and R2 both are the register that have a tolerance 1%. So in this we have given like R1 is 1.2 kilo ohm. So this and this is varying 1%, right? So plus minus 1% of this thing, 1.2 kilo ohm, that means 1.2 plus minus 1 by 100 into 1.2, right? 1.2, that means 1.2 plus minus, so this is 0.012 kilo ohm, right? Okay. So if so 1.2 minus 0.012, so that means this r1 has some minimum value, that is 1.188 kilo ohm, and this R1 have some maximum value, max, this value is nothing but 1.212 kilo ohm. So this R1 resistance varies from 1.188 kilo ohm to 1.212 kilo ohm. So similarly we should calculate the value of the R2. So R2 is nothing but 15 kilo ohm plus minus 1% of that, that means 15 plus minus 1 by 100 into 15, that is 15 plus minus 0.15 kilo ohm, right? So this R2 value, this also varies from minimum, so 15 minus 0.15, which is nothing but 14.85, right? 85 kilo ohm to this R2 has some maximum value, which is 15.15 kilo ohm. So this is the range of the R2. Okay, okay. So that is the non-ideal case. The op-amp is ideal, but the register is not accurately the value 15k and 1.2k. And now it is telling that what is the range of the VO. That means what is the output. Okay. So in suppose for this case, so we can see the op-amp is ideal. So op-amp is ideal. This is number one condition. Number two condition, it has a negative feedback. Negative feedback. So what do you mean by negative feedback? As I have discussed in the earlier classes also, this output voltage, that is VO, is connected somewhat like with a resistance to the inverting terminal. This is known as inverting terminal, and this is known as non-inverting terminal, non-inverting. So there is a path, or there is a we can say feedback path from output to the inverting terminal. So that means it is a negative feedback, right? Okay. So and the voltage is applying in the non-inverting terminal. That means it can be act as a non-inverting op amp, right? Non-inverting op amp. So the gain for the non-inverting op amp is basically VO divided by VI is 1 plus R2 divided by R1. So we have also discussed in the earlier classes, but okay, I am also discussing it in this class also. So as the op amp is ideal and it is connected in a negative feedback, so that means the virtual short concept holds. So these two refers that the virtual short concept holds. How it is holds? Like for generally, if it is an ideal op amp, so output VO is nothing but the open loop gain into the difference of the voltage that is applying in the inverting and non-inverting terminal, right? So this is AOL is basically the open loop gain, VO is the output, and VID can be written as V plus, that is the voltage applied across this terminal. This is V plus, and this voltage is nothing but V minus. Okay, so V plus minus V minus, that is VID, that is the difference voltage. Okay, so now if basically for the op amp the output is somewhat limited, and we can say V plus minus V minus is, from this equation you can write VO divided by AOL. So generally for the if the op amp is ideal, the open loop gain, that is AOL, this almost is equal to infinite. For the practical case this is not possible, but this is too much high, so in the ideal case we can say this is infinity. So if you put VO divided by infinity, then it turns out to be 0. That means V plus minus V minus is 0. That means V plus equal to V minus. So whatever we apply in the positive terminal, that voltage will apply at the non-inverting terminal, that voltage will apply in the inverting terminal as well, right? So these two are almost equal, so that means it is short. So basically it is not actually short, it is, that's why it is called as a virtual short. So this is the virtual short. That means whatever the V plus voltage we are applying, that same voltage will appear at V minus. Okay, so virtual ground concepts is like, virtual ground is a special case of virtual short. That means if we ground in any one of the terminal, that means V plus or V minus, any one of the terminal, then the other terminal will automatically be ground. That means from this case we can say that if V minus is equal to 0, then V plus is also equal to 0. Or we can say if V plus is equal to 0, that means that V minus is equal to 0. So this is the virtual ground. So virtual ground is a special case of virtual short. Okay, so for satisfying the virtual short, the op amp has to satisfy these two conditions. First one is the op amp is ideal, that means AOL tends to infinity. So op amp ideal means several things, actually three things are there. First thing is the open loop gain is infinity. Second thing is input resistance is very high. Input resistance very high means that op amp should not draw any amount of current, so no current will be flowing into the op amp, right? And the third case is the output resistance is almost tends to 0. That is output resistance is almost 0. So whatever the voltage that is amplified, that the same voltage will apply in the output VO. Okay, so these three cases are the most important cases in the for the ideal op amp. So this is the ideal op amp, and also it is connected in the negative feedback, so that's why we can write this as a we can consider it as a virtual short condition. So now what is happening, so here V plus and V minus should be at the same potential. Now 50 volt is applying over here. Okay, so I am generally analyzing this circuit. So if we analyze this circuit, so Vi, so V plus is equal to this. V plus is nothing but Vi, this voltage. Okay, Vi, and so V minus, according to the virtual short concept, that should be also equal to V plus, that is nothing but Vi, right? So this potential is nothing but Vi, and now it is ground. So here it is ground, so some current will be flow in this side. This is Vi potential, this is ground potential, so this current will be nothing but Vi divided by R1, right? This is R1. And so as we have already told, like op amp is ideal, so no current will be flowing in the op amp terminal, so this entire current should flow through this resistor. Okay, so as the current flow through the resistor, so there will be some potential drop, so this potential drop will be Vi, sorry, capital Vi divided by R1 into R2. Okay, and this, that polarity should be here plus and here minus. So the output voltage Vo can be written as Vo is nothing but this voltage means V minus, and then plus, here it is plus into Vi into R2 divided by R1, and V minus we have already calculated, this is equal to Vi, so it is Vi plus Vi into R2 by R1, right? If we take Vi common, that means 1 plus R2 by Ri. So the gain of the op amp Vo divided by Vi is nothing but 1 plus R2 by R1. This is the case of a non-inverting amplifier. Non-inverting amplifier means there is a negative feedback and we are applying the input in the non-inverting terminal, and in the inverting terminal we are just grounding it. Okay, so I have already discussed this in the previous case also, so that's why I have written this equation directly, that Vo by Vi is nothing but 1 plus R2 by R1. Now what is the question, that the resistance have some tolerances, so what will be the output, right? So this Vi is given like 50 millivolt, so Vo is Vi into 1 plus R2 divided by R1. So Vi is 50 millivolt into 1 plus, so Vo, it should be, it should also vary because R2 and R1 is varying. So when it will be maximum, so R2 is in the numerator and R1 is the in the denominator, so when there will be the R2 maximum value and R1 minimum value, then only it will then only the Vo output will be the maximum. So that means 50 millivolt into 1 plus, so what is R2 max value, we have already calculated, that is 15.15, and it is 1.188, so 15 point, so it is 15.15, that is R2 max, and R1 minimum value is 1.188. So this much, this is kilo ohm, right? So kilo ohm into millivolt, that means it will generate the value in the sorry, it will be in the sorry, this is kilo ohm and this is kilo ohm, so it will cancel out, so the answer will be in the millivolt. So 15.15 divided by 1.188 plus 1 multiplied with 50 millivolt, so that we will get 687 687.62, that much millivolt. So this is almost equal to 0.68, that is 0.687 volt. Okay, so this is the Vo maximum value. And what will be the case for the Vo minimum value? So Vo will get minimum value whenever this R2 has a minimum value, that is the numerator, so R2, it is R, sorry, so it is R2 that should have minimum value, and R1 that should have some maximum value, right? Maximum value, so it will be 50 millivolt 1 plus this maximum value is 15.15, R2 minimum value, so sorry, so it is 14.85 divided by the R1 value, this is 1.212, right? From here 14.85 this thing, and here it is 1.212. Okay, so how much it's coming? Let's see. 14.85 divided 1.212 plus 1 into 50, so that will be 662.62 millivolt. 662.62 millivolt, so that means 0.662 volt. So this VO output will be vary from 662 volt to 687 volt. So the correct answer will be, yeah, point B, that is 0.66 to 0.69. Okay. Okay, so this is the case where when the op amp is the ideal. If you have any doubt, you can stop me in any time and I will answer you. Okay. So yeah, so this is the case when the ideal op amp is an ideal, and also the resistance have some tolerance value. Then then the output is varying. So so we have calculated the thing. Okay. So for the next question, in the integrator circuit shown in the figure, so this is a basic configuration of an integrator circuit. So how the integrator circuit works, I am just this is minus, this is plus. So this plus terminal is in ground, and if we apply a capacitor over here, this is C, this is VO, and let's say this is VI and this is R. Okay, so let's consider the op amp to be ideal. Op amp is ideal, this is the first case, and the second case is that it has some negative feedback. So there is some negative feedback path, which is the capacitor is connected across it, through the capacitor the output is feedback to the inverting terminal, right? So these two conditions satisfied that the virtual short concepts can be applied. Okay. Okay, so here also the V plus will be nothing but V minus. Now V plus is connected to ground, so V minus will automatically be 0 volt. That means V minus is equal to V plus equal to 0 volt. Okay, so 0 volt. So if it is 0 volt, some current will flow through this. So some current will flow through this. So this current I can be written as I is nothing but VI. This is VI, and this is 0 volt. So VI minus 0 divided by R, that is VI by R. And as we have already told, the op amp is in ideal condition, so no current will flow through this side, so this entire current will flow through this capacitor. Okay, so now it will generate some voltage across it. Okay, so for capacitor we know I is nothing but C dV/dt. So this V is nothing but, so here it is ground. Okay, so the voltage here it is ground 0 and here it is V0, right? So this C dVc/dt you can say, or C d dt of this is 0 minus V0, right? Because the voltage across the capacitor is, here it is 0 volt and here it is minus V0, so that will be minus C d V0 dt. So if we calculate what is the value of dV0, so dV0, sorry, so now so this is the current that is flowing through the capacitor and this is the current that is flowing through the resistor. So both should be same, because the current through the op amp is 0, the op amp is 0. So Vi divided by R should be equal to minus C dV0 dt, right? So what is dV0? dV0 is nothing but minus 1 by RC Vi into dt, right? And what is the value of V0? V0, if we integrate this dV0, then we get, so minus integration of minus 1 by RC into Vi into dt. So R and C are some constant value, so this is Vi dt. So basically this is a integrator circuit. Why this is integrated circuit? Because whatever the voltage we are applying at Vi, the integration of this input voltage will appear at the output. So this is known as the integrator circuit. So this is the basics integrated circuit that is shown in the figure, and the input is 8 volt peak to peak 1.2 kilohertz square wave. So in order to obtain 4 volt peak to peak output voltage, what is the value of R? So how we will solve this problem? So basically in the integrated circuit, what happens if we give any square wave? So suppose we are giving any square wave like this. So this is the input volt. So this is if we are giving this square. So if we are giving this thing, so what happens is it will integrate and it will generate the output, right? So this is a you can say that the input is a step function. So the integration of the step is the ramp. So this is the output, and it is a basically triangular wave, right? Triangular wave. So if we give square wave in the input, we are getting the triangular wave in the output, right? Okay. So in the question it is told, like in the integrator circuit shown in the figure, the input is an 8 volt peak to peak 1.2 kilohertz square wave. So mm, so yeah, so I'm drawing the input voltage. Okay, so we are giving 8 volt, the input is 8 volt peak to peak, right? So 8 volt peak to peak means it will vary from plus 4 to minus 4 volt. Okay, so 8 volt peak to peak. So this is minus 4 and this is plus 4. Okay, so and the frequency is 1.2 kilohertz. So if that is frequency is 1.2 kilohertz, that means 1200 hertz. So the time period of the signal is 1 divided by frequency, which is 1 divided by 1200 second. So this is the time period. So time period refers to this portion. Okay, yeah, so this portion. So this portion is t, which is 1 divided by 1200 second. Okay, so now it is in the question it is asked, in order to obtain a 4 volt peak to peak output voltage, what will be the R is required? So we know that the output of the voltage will be, so we are getting 4 volt peak to peak, that means it will start from 0, so it will get 4. So this is minus 4, that means here it is coming minus sign, right? So it will be opposite of this input voltage, because it is we are applying the Vi in the inverting terminal, right? So the output will be the negative of that, that means it will be in the negative side. Okay, so now it is telling like 4 volt peak to peak, that means from 0 to 4 it will get from 0 to 4. Okay, yeah, like that. Okay, so what is so in the from the circuit, how we can find out? So here basically this R dash and C in parallel. So if we, so R dash is 150 kilo ohm, and C, if so we should find out the impedance, which is nothing but 1 divided by j omega c, right? So or 1 divided by omega c you can write. So 1 divided by twice pi into f means the frequency is 1.2 into 10 to the power 3, that is this much kilohertz. 1 divided by omega into c, so the value of c is 50 nanofarad. So 50 into 10 to the power minus 9. Okay, yeah, so how much it's coming? So 1 divided by so it will be 50 into 2, that means 100. So 1.2 into pi into 100 into 10 to the power 3 into 10 to the power minus 9. This 3 cancels out, 3 and 2 5, so it means 10 to the power minus 4 in this side. So 10 to the power 4 divided by 1.2 pi. So let's calculate. So 10 to the power, sorry, 10 to the power 4 divided by, so okay, so it will come like 2652 ohm, that means 2.652 kilo ohm. So here the equivalent impedance will be 2.652 kilo ohm, and here it is 150 kilo ohm. So 150 kilo ohm basically too large, so it will draw a minimum amount of current. So that means here actually this is as I have already discussed, this is ground, so this will be also ground. So whatever current that is flowing through this vi through this path, the entire amount of current, almost entire amount of current will flow through the capacitor, because it has some low value of impedances, and here r dash is very high, that is 150k. So a minimum amount of current will flow through this, so we can neglect this r dash part. Okay, yeah. So in actual analysis of the circuit, we are ignoring this r dash part. So why we are ignoring it, I have already discussed. So it has a very high impedance, and here it has very low impedance, so the maximum amount of current will flow through this low impedance path. Okay, so if we are ignore this thing, so we have only this r and this 15 nf. So as I have already discussed, the output vo will be minus 1 divided by RC integration of Vi into dt, right? Okay, so this so now the value is, so here the Vi input signal is a square wave, that is 8 volt peak to peak signal. So that means it is minus Vi divided by RC, because it is fixed signal, into dt. Okay, and so now integration of dt. So if we consider only this part, only this positive part, when this vi will be high, so that means now, so this is 0, this is t, and this is t by 2. So this is t, this is t by 2. So from 0 to t by 2, if we are getting, so vo, that means output, so output will reach the value of minus 4. So it will be minus 4, because it is getting from 0 to 4, right? 4 volt peak to peak, so it will be minus 4 is equal to minus, so this is sorry, so okay, we ignore this part. So this is minus 1 divided by r into c means how much, 15 nanofarad, 15 to 10 to the power minus 9, into integration over vi dt. Integration of vi dt means whatever is the area under this curve, right? So what is the area of this curve? This is 4, and this is 4 into t by 2, right? T by 2. So it will be minus 1 divided by r into 50 into 10 to the power minus 9 into 4 into 1 divided by, what is the value of t? We have already calculated, t is 1 by 1200, right? 1 by 1200. So it will be 1 divided by 1200. So now this minus 4 and this minus 4 will cancel out, so r will be 1 divided by 50 into 2 into 1200 into 10 to the power minus 9. So if we calculate this, so 50 into 2 into 1200 into 10 to the power minus 9, and inverse of this 1 divided by answer, which is 8333.33 ohm. So that much ohm, so that is 8.333 kilo ohm. So if the resistance value is this, then only the output will get 4 volt peak to peak. So in order to obtain a 4 volt peak to peak output voltage, the resistance R should be 8.33 kilo ohm, right? Okay. So you should know how we analyze the problem. So I am just repeating once more, that is the output voltage. We have already decided the what is the value of the integrator, like the output voltage will be minus 1 by RC over vi, integration of vi dt, right? So now whatever we are getting the output, that is minus 4. So minus 4 is equal to minus 1 divided by r and the value of c, and this integration of vi dt is nothing but the area under the curve of the vi. So we are considering till t by 2. So it is so we are getting t by 2, and this is the value is 4. The input voltage is 4 volt. So by calculating this, we are getting 8.33 kilo ohm, right? Okay, so I'm moving forward to the next problem. Consider the integrator circuit shown in the figure. The input voltage is a 5 volt peak to peak square wave with frequency range 1 kilohertz to 2 kilohertz. Okay, so there is a so this problem is the same problem like previous. So there is an integrator and the input voltage is 5 volt peak to peak square wave, right? So if we draw, so this is t and this is vi. So this is 5 volt peak to peak. So if this is so the 5 volt peak to peak means this is 2.5 and this is minus 2.5. This is the value of vi, and so square wave with frequency range. So this frequency is from 1 kilohertz to 2 kilohertz. So 2 kilohertz, and here it is 1 kilohertz. That means the time period is, so time period is 1 is, for one case it is 1 divided by 1 kilohertz. That means 1 divided by 1000 second, and for another case it is 2 kilohertz. That means 1 divided by 2000 second. 2000 second. Okay, that means the time period should be 1 divided by 2000 second, from 1 divided 2000 second to 1 divided by 1000 second. Okay, and now what is telling, we want to be able to adjust the output voltage to 5 volt peak to peak, right? So output voltage will be, it will start from 0, the output voltage, and it will go to 5 volt. So that means here, okay, so this is minus 5, right? So 5 volt peak to peak, and then it will again go to 0. It will again go to 0, like that. Also again in the next cycle it will go till minus 5, and then again it will go to 0. Okay, like that. Okay, so we want to able to adjust the 5 volt peak to peak of in for any frequency between this 1 kilohertz 2 kilohertz in the above range. So what should be the value of r? So what should be the value of r, so that we can adjust the voltage to the 5 volt peak to peak for the entire frequency range from 1 kilohertz to 2 kilohertz, right? Okay, so now how we will solve this problem? We have already know that this I1 in the from the earlier case, this v0 is minus 1 by rc vi dt, right? So we have already know v0 is minus 1 divided by rc integration over vi dt. So for the first case, what we are getting, so this for the first case, so first case means we are considering f equal to 1 kilohertz. Okay, for the 1 kilohertz case, so this vo is nothing but minus 5 is equal to minus 1 divided by rc. R value we need to determine, c is 50 nanofarad, that is minus 9 into vi. It is a square wave, so it is constant, so it will go out go uh, go to the left side of the integration. That means vi is 2.5, right? For this period it is 2.5, so this is t by 2 and this is t, right, like earlier cases. So it will be 2.5 into t by 2, right? So negative will cancel out, 2.5 and 5 cancel out, it will be 2. So r will be nothing but 1 divided by 2 into 50 into 10 to the power minus 9 into 2, and t is for 1 kilohertz case, t is 1 divided by 1000, right? So it will be 1000. So what is the value of this? If we calculate, so 2 into 50 into 2 into 1000 into 10 to the power minus 9. So it will be so this 50 and 2 means it is 100, and this is 3 and 2 5, that means 10 to the power minus 4, that means 10 to the power 4 divided by 2, that means 5000 ohm. Okay, so this will be 5 kilo ohm. So in the first case, the resistance value is nothing but 500 ohm or 5 kilo ohm. Okay, for the second case, the frequency is 2 kilohertz. So now we will put the same value, like minus 5 is minus 1 divided by R into C, which is 50 into 10 to the power minus 9 into, this is also 2.5, and now the value of T will be changed. So this minus and minus cancels out, 2.5 and 5 cancels out, and R will be nothing but 1 divided by 2 into 50 into 10 to the power minus 9 into 2 into, this is 1 divided by 2000, right? So it will be 2000. So earlier it was 5000 ohm, now it will be divided by 2, that means it is 2500 ohm. So that means 2.5 kilo ohm. So if we vary the resistance, from 2.5 kilo ohm to 5 kilo ohm, then we will get the 5 volt output, peak to peak output, for the entire range, that is 1 kilohertz to 2 kilohertz, right? So the correct answer will be answered B. This is minus 2.5 kilo ohm to 5 kilo ohm. Okay. Okay, so moving forward to the next question. So for the circuit shown in the figure to work as a difference amplifier, what value of resistance is required? So what do you mean by the difference amplifier? Okay, so I will discuss some part of the difference amplifier. So difference difference amplifier. Okay, so suppose this is R4, this is R3, this is V2, and this is R2, this is R1, and this is V1, and this is V. Okay, so we are applying some voltage like V1 voltage over here and V2 voltage over here. V1 voltage in the inverting terminal, and V2 voltage in the non-inverting terminal. So the difference amplifier means that the output should be proportion to V1 minus V2. So whatever the difference in the input signal, that will be amplified and we will get it as an output. Basically you can say VO is nothing but some gain. So this is gain into multiplied by the difference of the input. So that means it is a difference amplifier, right? Okay, so now how we can calculate? So here this V plus voltage is nothing but V2 into R4 divided by R3, and now it has a negative feedback over here, so V minus will be the same as a virtual short concept, so it will be V2 into R4 divided by R3. So it has some voltage, so there will be some flow of current, which is the current. If we consider it as I, so I will be nothing but V1 minus V minus divided by R1. So that means, and okay, so there will be some V minus will be like this, and the same amount of current will flow through this terminal, because the current through the op amp is 0. So this I will flow through this terminal, so this will be plus and this will be minus. So VO will be basically this V minus and minus of I into R2, right? So V minus is, we have already calculated, this is V2 into R4 by R3 minus the current I, which is V1 minus V minus divided by R1 into R2, right? So V2 into R4 by R3 minus this is V1 into R2 by R1 plus there it will be V minus. Okay, so V minus is nothing but V2, so V2 into R4 by R3 into R2 by R1, like that. Okay, so if we simplify this thing, so we will get that VO, if VO is nothing but R2 by R1 into V2 minus V1, if we consider that R4 by R3 is equal to R2 by R1. So if we consider this R4 divided by R3 is equal to R2 divided by R1, then we will get some gain, that is R1 R2 divided by R1 into the difference of the input. Okay, so as I have already discussed here, that this VO, that is the VO, this VO is nothing but gain into V1 minus V2. So here also, if this condition satisfies, then also we are getting the output voltage is proportional to the difference of the input voltage. So then this can work as a difference amplifier. So this is the main concept behind the difference amplifier. So now in the question it is asked that in this circuit shown in the figure, to work as difference amplifier, what value of R is required, right? So this R is required. So how we can calculate? So we can calculate in from this thing, from this manner also, or okay, I will go through this ones. So here the voltage V plus will be, so here the V plus value will be Vy2. I'm considering this as V2, okay, and this is V1. Okay, so V2 into R divided by R plus 1. Okay, so this voltage is V divided by R. So this same voltage will appear in the opposite terminal also. This is V minus terminal also, because of virtual short concept, R divided by R plus 1. Okay, so now what we can see, this, so this voltage is V2 minus this, so V1 minus V2 into R divided by R plus 1 divided by 2.2. so this much current will be flowing through this. This is the potential, this is V minus, this is the potential, and this is V1. So this current will be equal to, there will be no current flowing in the op amp, so that current will be equal to the same voltage like Vx, which is nothing but V2 into R divided by R plus 1 minus VO divided by 33. Okay, so from here we get that, so this VO will be, so if we consider this thing, okay, so once V2 into R divided by R plus 1 minus VO will be 33 divided by 2.2 into V1 minus V2 into R divided by R plus 1. Okay, so if we move VO in one side, then we are getting 33 divided by 2.2 V1 minus V2 into R plus 1, this thing, plus V2 into R divided by R plus 1. Okay, oh sorry, so okay, so that will be minus sign and this will be minus. Okay, yeah, so if we consider this VO, that will be minus V1 into 33 divided by 2.2 plus, if we take this V2 common, V2 into r divided by r plus 1 common, then we will get 1 plus 33 divided by 2.2. Okay, so that means v0 will be proportion to v2 minus v1 if this coefficient is equal to this coefficient, this coefficient. So that means 1 plus 32 divided by 2.2 into r divided by r plus 1 is nothing but equal to 32 divided by 2.2. So it will be 35.2 divided by 2.2 into r divided by r plus 1 equal to 33 divided by 2.2. Now 2.2 cancels out. So now 35.2 r equal to 33 r plus 33. Okay. So basically we are getting 2.2 r equal to 33. So r is nothing but 33 divided by 2.2. So 33 divided by 2.2, if we do, we get 15. So 15 kilo ohm. So the value of the R2 will be 15 kilo ohm, for which we are getting this thing as a difference amplifier. Okay. Okay. So this is the thing. And there are some alternate approach also. Alternate approach is nothing but you should have remembered, right, that R4 divided by this, if this is R4, this is if this is R2, this is R1, this is R4, and this is R3, then you should remember that R4 by R3 should be equal to R2 divided by R1. So from there also you are getting the value of R4 equal to R2 into R3 divided by R1. R2 is what? R2 is 33 into R3. R3 is 1k, so it is 1 divided by R1. R1 is 2.2k, so which is 15 kilo ohm. So R4 value will be 15 kilo ohm. Okay. So this is the thing, that how this op-amp can act as a difference amplifier. So the value of resistance R will be 15 kilo ohm. Then only it will act as a difference amplifier. Okay. Okay. So I am moving to the next question. A differential input signal of 10 millivolt peak to peak. That means a differential input signal. That means this Vi1 minus Vi2 is equal to 10 millivolt. Vi1 minus Vi2 is 10 millivolt. This 10 millivolt, a differential input signal of 10 millivolt peak to peak, is applied to the circuit shown in the figure. So what is the value of V0 from peak to peak? Okay. So how we can determine? So Vi1 minus Vi2 is 10 millivolt. So here, so basically how we apply this thing? So suppose if there is some resistance connected across it, and here we have some voltage, there will be also some voltage drop, and by this thing we are just applying the Vi1 is greater than Vi2, like that. So okay, so here in this case what is happening, so it is a negative feedback, so virtual short concept holds. So this terminal will be Vi1, and similarly for this op amp also, this is Vi2, the non-inverting terminal, so the inverting terminal will be Vi2, and this terminal Vi1 is connected over here, so this is Vi1, and this terminal is Vi2. Okay, yeah, so this is Vi1 and this is Vi2. Now what is happening, this, so the current flowing through this, if we consider it as small I, so the current flowing through this resistor, that is 220 ohm resistor, is Vi1 minus Vi2 divided by 220 ohm, right? Okay, so Vi1 minus Vi2 is what? So Vi1 minus Vi2 in the given question, it is 10 millivolt, right? So 10 divided by 220, that much milliampere current will flow. So what is the value of that? 10 divided by 220 is 0.045 milliampere. This much current will flow through this side. Now see one thing, so that this current, no current will flow through this side. Okay, so the entire current will so this I will flow through this side, and also there should not be any current flowing through this side. So this side current as the op amp is ideal, no current will flow through this, so this entire I will flow through this side. Okay, so this is, if this is V minus and if this is V plus, if we consider this thing, or if we consider this as V1, okay, and this is considered as V2, then what is the what we are getting across that Vi minus V2? So V1 minus, so 9.1 kilo ohm, and there the same current is flowing, so there will be some drop, 9.1 k into this current, that is 0.045 minus this Vi1. So this is I, that is 220 ohm into 0.045, so 220 ohm means 0.220 kilo ohm, right, into this milliampere, minus this is 9.1 into 0.045 minus V2 will be equal to 0. This is V2 and this is V1. Okay, so we are getting V1 minus V2 as 9.1 into 0.045, this is coming 2 times, plus 2.220 into 0.025 is nothing but this current flowing. This is this thing, the difference, that is 10 millivolt. So 10 millivolt means 0.010. Okay, so now what we are getting, 9.1 into 2 into 0.045 plus 0.010, this is 0.829 millivolt. So now this V1 minus V2 is 0.829 millivolt that we got. Now if we reduce the circuit like this, so okay, so now that means so this is also a difference amplifier. So this is basically a difference amplifier. So what is happening, so as I have already discussed in the previous problem, so by this resistance only we are we just apply some difference voltage in the input and we apply to the op amp, right? So by this configuration, here it is like this resistance, this resistance, this resistance, by this configuration only we generate this V1 greater than some amount greater than V2, and then that difference will be detected by this op amp and got amplified and we get it as an output. Okay, so now this is an difference amplifier. So what we have already discussed, for the difference amplifier the gain VO is nothing but R2 times R1 into V1 minus V2, right? If R4 by R3 is equal to R2 by R1, as I have already discussed. So here R4 is 22, and so 22, this is 22, and R3 is 10. So similarly here also R2 is 22 and R1 is 10, so it is satisfying, that means it is a difference amplifier. So this output VO will be R2 divided by R1, that is 22 divided by 10 multiply with this difference voltage. Okay, 0.829 millivolt. So how much it's appearing, 0.829 into 22 divided by 10, so this is 1.8238, sorry, so this thing will appear as volt, this much volt. Okay, because this is in sorry, this is in kilo ohm and this is in milliampere, so the amount so the unit will be volt, so this much volt will appear, so 1.8238 volt. So the correct answer will be 1.84. This is the nearest answer. Okay, so 1.84 volt. Okay, so see one thing, that whatever we are applying as a differential input, that is V1 minus V2, is just only 0.829 volt, but by this difference amplifier we are detecting this difference and we are amplifying it and we are getting 1.8238 volt, and according to this we can control, or we can measure measure this differential input, right? So the basic use of this difference amplifier is as a transducer. That means if suppose there is some pressure sensor, so in the pressure sensor, what is happening, like if there is some change of pressure, so that pressure we are converting it as a change in the resistor value, and as a result some differential voltage will generated, and this small amount of deviation is enlarged using the amplifier, and it is coming in the output, and according to this we can control and we can measure, and we can control the that pressure, like that. Okay, okay, okay. So I'm moving to the next problem. So next problem is pretty much the same thing, like in the circuit shown in the figure, what value of R is required to obtain a gain with magnitude 50. Okay, so what is the value of R that is required? So this R is not known. Okay, so like in the previous case also, if this is Vi1, this is also Vi1, because this is virtual short. Yeah, and this is Vi2, so this thing terminal will also be the Vi2. So same thing goes here also, Vi2, and this is Vi1. Okay, so now the current through this, that means the current through this terminal I, so I will be Vi1 minus Vi2 divided by R. Okay, divided by this resistor. So this much current will flow. So now if we consider it as V1, if we consider it as V2, the same I have already discussed, the same amount of current, that is same amount of I will come from this side, will go from this side, because there should not be any current that is flowing here or any current that is flowing in this op amp. So the entire current will be through this. So now we need to determine what is the differential input voltage, that is V1 minus V2, that is being applied to the difference amplifier, right? Okay, so V1 minus 9.1 k into I means this thing into I. Okay, let me write the whole equation, minus this is I into R, minus there should be also 9.1 k into I. Okay, minus V2 equal to 0. So we need to determine the differential input voltage, so V1 minus V2. So now V1 minus V2 is what? It is 9.1 into I into 2 plus I into R, I into R. So it is 9 into 1 into 2. What is the value of I? This is Vi minus Vi1 minus Vi2 divided by R, plus this is also Vi1 minus Vi2 divided by R into R. This R cancels out. So if we take Vi1 minus Vi2 common, then we will get 1 plus 9.1 into 2 divided by R. So this is the, yeah, so this is the differential the differential input voltage that is applied to the difference amplifier. Difference amplifier means this amplifier. Okay, so now what will be the gain in the difference amplifier? The VO will be nothing but, as I have already discussed, R2 divided by R1 into what is the differential input voltage. So R2 minus R1 is 22 by 10, and V1 minus V2, we put this formula. This is Vi1 minus Vi2 1 plus 9.1 into 2 divided by R. Now we have to determine the gain, that is VO divided by VI1 minus VI2, right? So VO divided by VI1 minus VI2 is 22 by 10 into 1 plus 9.1 into 2 divided by R. And now this VO divided by this gain is 50. We should get 50 magnitude of gain. So from here 50 is 22 divided by 10, 1 plus 9.1 by 2 by R. So 1 plus 9.12 by R is equal to 500 divided by 22. So 9.1 into 2 by R is 500 by 22 minus 1, and R will be 9.1 divided into 2 divided by 9.1, 22 minus 1. So what is the value? Let's see. So it will be 500 divided 22 minus 1. Yeah, into 2. 0 point, so R will be 0.837 kilo ohm. So this will be 0.837 kilo ohm, that means 837 ohm. Okay. So the nearest answer is 840 ohm. So this R value should be 840 ohm, so that the total the gain of this amplifier, the total amplifier is 50. Okay. So the you can interpret this as also that this total thing now it's working as a difference amplifier, right? So whatever you are applying in VI1 and VI2, that is the differential input, and that is getting amplified and it is generating VO as an output, and that is 50, that the gain is 50. That means if VI1 minus VI2 is suppose 1 millivolt or suppose 0.1 volt, then the VO output will be 0.1 into 50, right? So 5 volt. So this 0.1 volt is amplified by this total the difference amplifier, and it is getting 5 volt, and then we can easily measure it. Okay. Yeah. Okay. So the next problem. Okay, so in the difference amplifier shown in the figure, R1 is 1% larger than its nominal value, while the other resistance are equal to their respective nominal values. What is the common mode gain of an amplifier? Okay, so what do you basically mean by the common mode gain of an amplifier? Suppose there is some amplifier, so it has some signal that is plus and this is minus. Okay, so here it is V plus and here it is V minus. So suppose for any amplifier we can write the output voltage VO is nothing but AD VD plus AD VC. That means AC VC. This is the output of an op amp. So this AD means differential mode gain or differential gain. VD is nothing but the differential signal, means VD is V plus minus V minus. This is the difference signal. That is the difference signal that is applied. AC is common mode gain, and this VC is half of V plus minus V minus. Okay. V plus plus V minus. Okay, so common mode gain, you can say it in this way, like suppose there is some noise, there are some noise due to some due to something, some other thing, there is some noise. So the same amount of noise will affect both of the terminal of the op amp, right? So here also it will affect and here also it will affect. Okay, so suppose there are some noise that is the input to the amplifier, so that noise will affect not only one terminal but both terminal also. So you can say like this, suppose there is some source of noise that is applying to the both terminal of the both the input terminal of the op amp, inverting terminal as well as non-inverting terminal. So this noise is a common mode signal. So how this common mode signal can be determined? So as I have already discussed, the output voltage of an op amp can be written as AD into VD plus AC into VC, where AD is the differential gain, that is the gain due to the differential input. Differential input means whatever the difference of the voltages that is applying V plus minus V minus, this is the difference signal, that is the difference mode signal. And the common mode signal is half of V plus plus V minus, that means the entire amount of this signal is appearing in the both of the terminal, the same terminal. So this has also some gain, this is referred as common mode gain. Okay, okay. So now, so if the differential amplifier shown in the figure R1 is 1% larger than its nominal value, then while all other resistance are equal, then what is the common mode gain of the amplifier? So common mode gain, how we can say? So as I have already discussed, the common mode gain is nothing but half of V plus plus V minus. Okay, so whatever voltage we are applying, like this. So we can solve it like this. Suppose 1 volt voltage is applying through this, so the same 1 volt will apply through this also, because it's a common mode signal. So the for the both signal there is some source, so from this source only this 1 volt is coming, right? So vi1 and vi2 are considering is 1 volt, and then we are finding out what is the value of v naught, then we can get it is a common mode gain, right? Okay, so this is Vc, right? Vc is half of V plus plus V minus. Okay, so how we can calculate? So here the potential across this terminal will be let us consider V plus is equal to Vi2 into 20 divided by 21.2. Okay, so it will be 20 divided by 21.2. This is 0.94339. This much Vi2. Vi2 is 1 volt, that means 0.94339 volt. This thing. Okay, this thing 0.039. So the same thing will appear here also, because it's a virtual short concept, because it's ideal op amp 94339 volt. So there should be some current over here, so that the current will be I, if it refers to I. So I will be 1 minus 0.94339 divided by this resistance, that is 1.2k, this resistance, and the same amount of current will flow through this, because no current will flow into this op amp. So this VO will be nothing but this voltage is 0.94339. Oh, one thing I have done mistakenly. 1% larger than its nominal value. So R1 is no more 1.2 kilo ohm. So R1 is changes to 1.2 plus 1% of 2. That means 1.2 by 100, right? So 1.2 plus 0.012, that means 1.212. So it will be 1.212. Okay. So this output voltage will be this voltage, and then this is minus this drop 20 into 1 minus 0.94339 divided by 1.212. Okay, so how 1 minus 0.94339 divided 1.212 multiplied with 20 and then 0.94339. So it will be 9 point, so the answer is 9.231 into 10 to the power minus 3. That means 0.009231. This is the answer. So this is the output VO. So here, so what is the, so this output, this VO is known as a common mode gain, because we have not applied any differential input, we have not applied any signal. The 1 volt we are considering it, this is applying in the both of the terminal. So this is a common mode signal, 1 volt. So the so what is the common mode signal that we have calculated? 1 plus 1, that means 1 volt. 1 volt is we are applying and we are getting this much volt in the output. So the common mode will be this VO divided by V1, which is nothing but 0.009231. So this is the answer. This is close to this one, so this will be the answer. So this is the, we can say, common mode gain, okay, of this amplifier. Okay, so here in the next question, similarly it is like the previous one. Now the R2 is varying, so R2 will be 1% larger than its nominal value. So 20k plus 20k into 1%. Okay, so 20k plus 0.20, that means 20.2 kilo ohm. So 20.2 kilo ohm is applying. So now here the voltage V plus is Vi2, which is 1 volt, because the same thing, we are applying a 1 volt signal to both the terminal. Okay, so this 1 volt signal, now it is going to this, so that means 1 volt signal, this is 1 volt into 20 divided by 21.2 by voltage divider rule. So here we are getting 20 divided by 21.2, which is 0.94339. okay, so this much volt. So V minus will be the same, so V minus will be the same, 0.94339, and here also the current will be same, like 1 minus 0.94339 divided by 339 divided by 1.2k. So that current will be flow through this side, so it will be plus, it will be minus. So this V0 output will be this voltage is this thing, so 0.94339, this thing, and then minus of the current, 1 minus 0.94339 divided by 1.2 into this R2. R2 is 20.2 kilo ohm now, so 20.2. So let's calculate it. So 1 minus 0.94339 divided by 1.2 multiplied with 20.2, this thing, 0.94339 minus answer. So this is minus 9.5 into 10 to the power minus 3. That means it will be minus 0.0095, like that. So the correct answer is, the nearest answer is minus 0.0094. So this is the answer. So you should know that what is the meaning of this common mode gain. So now this common mode gain means, if we just put the amplifier in this configuration, suppose here if we connect plus 15 volt, and here if we connect minus 15 volt, and we have just connected these resistors, but we have not applied any input voltage Vi1 and Vi2, then also this Vo will get this value, that means minus this volt, this value, this is the common mode gain. So what is the input signal? So this Vo is nothing but AdVd, as I have already discussed, plus ACVC, right? ACVC. So here we are not applying any voltage, so this is 0, so that means it's equal to ACVC. so this AC value is nothing but this value. So whatever there is a common mode signal that will apply, that is appearing in this both of the terminal, that got multiplied with this common mode gain, and that will come in the output voltage. Ideally the output voltage should come as 0 volt, but it will not come 0 volt. Certain value, a certain amount of voltage that will come. So this is the thing, this is the meaning of this common mode gain or common mode amplifier. Okay, yeah. So in the next question also it is asked, like in the difference amplifier, now the R3 is 1% larger, that means now it is changed to 1.2 plus 0.012, that means 1.212, right, kilo. So what is the voltage? Again V plus is nothing but 1 volt, Vi2 means 1 volt, 1 into 20 divided by 21.212, right, voltage divider. So how much it is? 20 divided by 21.212, so this is 0.9428. okay, so this V minus will be the same because it's virtual short concept, 0.9428. so now this is 1 volt, so some current will flow in this side, so this I will be 1 minus 0.9428 divided by 1.2, and the same current will flow through this side because no current will flow in this op amp, right? So now this VO output will be this V minus is this voltage 0.9428 plus, sorry, minus, because this is positive sign, this is negative sign, right? So this voltage minus this voltage equal to VO. So minus this thing, this current, that is 1 minus 0.9428 divided by 1.2 multiply with this resistance, right, 20. So let's see what is the value that is coming. So 1 minus 0.9428 divided by 1.2 into 20, so 0.9428 minus 1 minus 0.9428 divided by 1.2 into 20, yes, 0.9428 minus, yeah, it is minus 9.47 into 10 to the power minus 3. So the correct answer will be option D. Okay. Okay. The next question, it is also the same question. In the differential amplifier shown in the figure, R4 is 1% larger than its nominal value. Now this is larger. So instead of 20k, it is 20 plus 20 into 1 divided by 100. That means 20.2 kilo ohm. This thing. So what is the common mode gain? The same thing. So here V plus will be Vi2 is 1 volt into 20.2 divided by 20.2 plus 1.2, right? So this is 21.4, right? Okay. So 21.4. 20.2 divided 21.4. Okay. So this is 0.9439. Okay. So this is also, this will be the also same, V minus is equal to 0.9439. So here some current will be flowing, that current will be flowing through this side. So V0 is nothing but 0.9439 minus of this current, this is 1 minus 0.9439 divided by 1.2, right, 1.2, okay, multiplied with 20. Okay, so what is the answer? 1 minus 0.9439 divided 1.2 multiplied with 20, this thing. So it will be 9.32 into 10 to the power minus 3. So it will be 0.0093. So yeah, so correct answer will be option B. Okay, so these are the pretty much the same problem that we have discussed. Now now this is some other problem. In this difference amplifier shown in the figure, R1 is 1% larger than its nominal value while all other resistance are equal to the respective values. What is the CMRR? So CMRR, what do you mean by CMRR? CMRR refers to common mode rejection ratio. Common mode rejection ratio. It is an inbuilt property of an op-amp. How it can determine? Suppose there is some op-amp. So here is some voltage V1, sorry, V1 and V2 we are applying here. So what I have discussed, that VO will be nothing but AD into VD plus AC into VC, right? Where VD is the differential voltage, which is V1 minus V2, and AD is the differential gain, Similarly, the VC is the common mode signal. This is a differential signal or differential voltage. This is the common mode signal or common mode voltage. Common mode voltage how much? Half into V1 plus V2, and AC is the common mode gain. Common mode gain. Okay, yeah. So now CMRR, that is common mode rejection ratio, can be defined as AD divided by AC. By doing AD divided by AC, we get the CMRR. Now what is telling that what is the value of CMRR in this case? So now here the V plus is nothing but this VI2, that is VI2 into multiply with 20 divided by 20 plus 1.2, that is 21.2 kilo ohm. So that means this is the 20 divided 21.2, 0.9433. So 0.9433 Vi2. Okay, so now whatever the current flowing through this, that is Vi1 minus 0.9433 Vi2 divided by 1.2k. So this same amount of current will be flow through this side. So 0.9433 V2 minus This is V naught, the output voltage, divided by 20k. So 20 divided by 1.2 Vi1 minus 0.9433 Vi2 is equal to 0.9433 Vi2 minus V0. V0. If we move V0 to the other side, we get V0 is equal to 0.9433 Vi2 into 20 divided by 1.2 plus 0.9433 Vi2 Vi2 minus 20 divided by 1.2 Vi1 equal to, so now this voltage, how much voltage? So this value will be 20 divided by 1.6 1.2, this is 16.66 Vi1. So 16.66, and this thing will be 16.66 Vi2 minus Vi1. So this V0 divided by Vi2 minus Vi1, that will be 16.66. So this is the thing which is known as differential mode gain. This is AD, or we can easily know. So this is a differential amplifier. This is a differential amplifier. So in the case of a differential amplifier, we have already discussed the gain will be R4 by R3 or equal to R2 by R1. By this also we can easily determine this thing. So 20 divided by 1.2, if we do this 20 divided by 1.2, so for this thing it is 16.667, right? So it is the same thing that we are getting. Okay, so this is the differential mode gain. And what is the common mode gain? Common mode gain, when we put the Vi1 and Vi2 both 1, and we have determined this thing earlier only, that uh, this thing, when R1 is 1% larger, so it is 0.0093. So AC is 0.0093. So here the AD is 16.66 and AC is 0.0093. So in this case the CMRR will be AD divided by AC. So 16.66 divided by 0.0093. So 16.66 divided by 0.0093, this thing equal to, so this thing so now in the question it is given like given what is in the answer, it is given what is the value, it is in dB. So CMRR, if we want to calculate it as dB, as it is a voltage gain, so that means it will be 20 log 10 AD divided by AC. So that means 20 log 10, and then it is 16.66 divided by 0.0093. So 16.66 divided 0.0093, log of that multiplied with 20, 65.06 dB. So the correct answer will be 65 dB. Okay, so this is the same thing. Okay, yeah. Okay, So in the question number 12, the op-amp in the circuit shown in the figure is ideal except an offset voltage VOS equal to 5 millivolt. What do you mean by offset voltage? Offset voltage means whatever we have considered so far. So this is a non-ideal op-amp. So non-ideal op-amp. Non-ideal op-amp. So in the ideal op-amp, we have seen like this VO output is AOL VID. I have already discussed. So AOL V plus minus of V minus, and this V plus minus V minus is VO divided by AOL. AOL is so large that it is tends to 0. That means V plus is almost equal to V minus, but it is the ideal case. It is almost equal to these things, but practically this is not possible. So there are some non-idealities present. So V plus cannot be almost equal to the V minus. That means if if any one of these V plus or V minus is ground, that is 0 volt, the other have certain a small amount of value. So this value is known as the offset voltage. So here it is told like VOS equal to 5 millivolt. That is the offset voltage is nothing but 5 millivolt. So now if it is 5 millivolt, then it can be plus 5 millivolt or it can be minus 5 millivolt in the both of the side. So here it is plus 5 millivolt. So the current flowing through this thing will be 5 millivolt, that is plus minus 5 millivolt, and this is the ground. So this divided 1 by 1.8, this is the current, and that current should flow through this side. So this side means equal to VO minus this thing, that is plus minus 5 volt, 5 millivolt, this thing divided by 20, right? So we can write VO divided by 20 is equal to plus minus 5 millivolt 1 divided by 1.8 plus 1 divided by 20, right? Okay, so now VO is 20 into plus minus 5 millivolt into 1 divided by 1.8 plus 1 divided by 20. So if we calculate this, 1 divided by 1.8 plus 1 divided by 20 into 20 into 5, this will come plus minus 60.55 millivolt. So that is close to the 61 millivolt. So that will be the answer. So the op-amp circuit in the figure is idea offset voltage. So due to the offset voltage, the VO is like this. So that means in this configuration, in this op-amp, so ideally this negative terminal is grounded, positive terminal is also grounded. That means if it was in ideal condition, if what is the interpretation, if it is in the ideal condition, if we connect like plus 15 volt minus 15 volt, this VCC, this is VCC, this is minus VCC. If we connected this terminal and connect the input terminal like this, so if it was ideal, then it was 0 volt, and it is also 0 volt. So 0 volt and 0 volt, that means no current will be flowing through this. So this V naught will be, so if there is no current flowing through this, no current flowing through this, there should not be any current flowing through this. So the drop across will be equal to 0. So this V0 should also is equal to 0, should be also equal to 0. But in the practical scenario, that is not the case because of the non-idealities present, such as offset voltage. Here some plus minus 5 volt is appearing, and if we configure if we just put these registers in the in this configuration without giving any input in the inverting non-inverting terminal, the VO output will be plus minus 61 volt. Okay, yeah. Okay, so the next question is, the op-amp in the circuit shown in the figure is ideal except for an input bias current IB and input offset current IOS. What is the worst case V naught? What is the magnitude of the worst case? Okay, okay. So now what is happening? Like, so ideal, it is also a similarly non-ideal case. So one of the non-ideal case is offset voltage that we have already discussed in the earlier problem. Another non-ideality problem is the current, the input bias current and input offset current, these both two things. So ideally the input resistance of the op amp should be very high, that means the current to the op amp is equal to 0. But practically it is not possible. Practically what happens, some of the current flow through this terminal, and this thing refers to non-ideality in the op amp. So in the non-ideal case, what happens, the input bias current that is IB, which is referred as half of, suppose I1 current flowing through this side, I2 current flowing in this side, this is half of I1 plus I2. This is the input bias current. And the input offset current can be written as I1 minus I2. This is the input offset current. These two things are the non-ideality case. So now here in the given question it is given half of I1 plus I2. So I1, either it can be like this I1 and it can be like I2, or it can be I2 and it can be I1. Okay, both of the cases are possible. Okay, so half of I1 plus I2 in the given question, it is given like 80 nanoampere. So I1 plus I2 is 160 nanoampere, and I1 minus I2, which is the input offset current, that is 15 nanoampere. So if we add this thing, these two cancels out, so I1 will be 160 plus 15 divided by 2. This is 87.5 nanoampere. Okay, just wait for a second. Yeah, sorry. Okay, so I1 is 87.5 nanoampere. Okay, so now what will be the I2? So now I2 will be 160 minus 87.5, this much nanoampere, right? So 160 minus this, it is 72.5 nanoampere. Okay, yeah. So I1 and I2 both are this thing. Let me see whether, okay, it's on only. Yeah. Okay, so this is 72.5 nanoampere, right? So now what is happening? So I1 and I2, and now this I2 is flowing through this and this I1. So this thing, so suppose so this I1 should flow through this op amp. So as this is the ground, so here also it is 0 volt, because there is not in the question it is not given like offset bias voltage, how much offset bias voltage is there. So if it is 0 volt, the plus terminal, it is also 0 volt, that is the minus terminal should also be 0 volt. So it is also 0 volt, that means what, that means there should not be any current flow in this R1 path, right? So the entire current I1, that will be supported by this R2, right? R2. So as I have already discussed, so in this negative terminal, that is the inverting terminal, it can be either I1 or it can be either I2. So case 1, if we consider it as I1, if we consider it as I1, then what is the value of VO? VO is nothing but I1, that is 87.5 into 20k. So how much it is? 87.5 into 20, which is 1.75 volt. So 1.75, sorry, it is millivolt, right? Because it is the nanoampere, that means 10 to the power minus 9, and it is kilo ohm, that means 10 to the power 3. So it will be 10 to the, if I multiply 10 to the power minus 6, that means it is coming as 1750 microvolt, that means 1.75 millivolt. Okay, yeah. And case 2 is that if we consider it as I2, then V0 is nothing but 72.5 into 20. So what is the answer? 72.5 into 20, that is 1450 microvolt, that means 1.45 millivolt. So now the worst case scenario, worst case means what is the greatest value of the v naught that can occur. So it will be 1.75 millivolt, right? Because it is greater than 1.45 millivolt. 1.45 is still tolerable, but 1.75 is much more than 1.45. So that will be the answer. Okay. Okay, the next question. The op amp in the circuit shown in the figure is ideal except an offset voltage, that is, this is plus minus 5 millivolt. So what is the value of V naught? What is the value of V naught? So now here it is not grounded, but here there is some resistances. Okay, so if there is some 5 millivolt is there, then there will be some current flow through this. If it refers to I, so I will be, so suppose this is plus minus 5 volt, so plus minus 5 volt minus 0 divided by 1.8 is equal to V naught minus plus minus 5 millivolt divided by 20k, right? Okay, so V naught divided by 20 is equal to plus minus 5 millivolt into 1 divided by 1.8 plus 1 by 20, right? So V naught will be 20 into plus minus 5 millivolt into 1 divided by 1.8 plus 1 divided by 20. So how much it will come? 1 divided by 1.8 plus 1 divided by 20 into 5 millivolt into this, so it will be plus minus 60.55 millivolt. So it will be near about plus minus 61 millivolt. Okay, so this is the answer. Okay, it is the last problem. The op amp in the circuit shown in the figure is ideal except an input bias current IB this, IOS this, the same thing. What is the worst case V naught? So it is same to the previous problem, but here the extra thing is, here also there is one resistor that is attached over here. Okay, so suppose here it is I1 and here it is I2. Okay, so input bias current, which is half of I1 plus I2, is nothing but 80 nanoampere, right? 80 nanoampere, right? So I1 plus I2 is 160 nanoampere, right? And then offset current is I2 minus, sorry, I1 minus I2, let's say I1 minus I2 is nothing but 15 nanoampere, right? So 2I1 equal to 175 nanoampere. So I1 will be 175 divided by 2. This is 87.5 nanoampere. And I2 will be 160 minus this, that is 72.5 nanoampere. So there will be two cases. Suppose case 1, I am solving the case 1. Case 1 is I1 is this and I2 is this. So if I2 is this, this is flowing through this side, so there will be plus and minus sign. So this voltage V plus will be, so this V plus will be minus 1.1k into this I2 means 72.5 nanoampere, so that much. So 72.5 into 1.1, this much microvolt, that is minus 79.75 microvolt, right? Okay, yeah. So now what happens is this V minus, okay, so now what happened is this V minus should also equal to minus 79.75 microvolt. So there will be some current flowing through this. So the current flowing through this thing, that is I is equal to 79, 0 minus of minus 79.75 microvolt divided by 1.8 K. How much nanoampere? This is 79.75 divided by 1.8, which is 44.30 nanoampere. That is the current flowing through this. So now the I1 current is flowing through the op amp. So the rest of the current is supported by this. So the rest of the current, that is, it is say it is I1, okay, and it is I2. So the I2 will be nothing but I2 will be this 87.5 minus 44.30, this much nanoampere. So 87.5 minus 44.30, okay, so 43.2. So 43.2 nanoampere current will be flowing through this. So this is plus, this is minus, so V0 will be, so whatever the voltage that is here, that is minus 79.75 microvolt plus this 43.2 nano plus 20, this much microvolt, okay, microvolt. So what is this coming? 43.2 into 20, okay, minus 79.75. So that is 784.25 microvolt. So that means 0.784 millivolt. So this is the V0 in the first case. So here, okay, it is not given in the answer. Okay, so in the case 2, let's find in the case 2 what is the case. So V plus will be, so like that only, 1.1 into this thing 87.5, that means 87.5 into 1.1 minus 96.25 minus 96.25 microvolt is there, right? So V minus will be equal to same thing, minus 96.25 microvolt. So now I1 will be 0 minus of minus 96.25 microvolt divided by 1.8 K, the same resistance, which is 53.47 nanoampere. So 53.47 nanoampere, now it is flowing. Now it is 53.57 nanoampere is flowing. So the rest of the current I2 will be, so here I2 will be 72.5 minus 53.47 nanoampere. 72.5 minus 53.47, so it is 19.03 nanoampere, okay, 19.03 nanoampere, right? Okay, so now this current will be flow through this resistance R2. So V0 will be minus 96.25 microvolt plus this 19.03 is flowing through 20 kilo ohm. So this much microvolt. So what is the answer? Minus 96.25 plus 19.03 into 20. So that will be 284.35 microvolt. That means 0.284 millivolt. So in one case it is coming 0.784 millivolt. In another case it is coming 0.284 millivolt. So here the correct answer will be 0.784. I think this answer is wrong. Answer C will not be the answer. The correct answer will be this, because this is higher, right? This is fluctuating mode. The output voltage is fluctuating mode, 0.784. So this will be the answer. Okay, so this is for the today's session. So I have completed all the things, like initially I have done with the op amp for the ideal cases, what it should be, right? Yeah, so if the op amp is ideal and then the resistor has some variance, like how much it can tolerate, or if there is some resistance differences, then how the output voltage is going to differ from its original value. And then I have discussed about the integrated circuit, how it works, and how we can find out for a particular frequency range. And in the next problem I have discussed with a variable frequency range how the value of resistance we can maintain so that the output peak to peak voltage remains constant. And then again in the next problem, next for the some problems I have discussed about the difference amplifier, how it works, and what is the effect of some resistance differences. The value, if the value of resistance differs, then how the output will be there, and what is the common mode gain, and then the CMRR, that is common mode rejection ratio. And at last I have discussed about some non-idealities, which is offset voltage, input bias current, and input offset current of the op amp. Okay, so this is all for today's session. If you have any doubt, you can ask in the discussion forum, or also you can ask me in the next class. Okay, thank you. So I am just stopping the recording.